All right, hello friends, and welcome to your Snow Day genetics video. Today I'm going to show you how to make this Punnett square for your own assignment that's due on Wednesday. So here we go. Okay, so one way to describe what I'm going to show you is a dihybrid cross, predicting the offsprings of a dihybrid cross. And that's one of the ways it's described in textbooks. What does this really mean? In simpler terms, if we are taking two double heterozygotes and crossing them together, it is a way to predict what their babies will look like. And in my example, I'm going to use dragons, but you can use any animal. That will be your assignment. So you need to pick two independent traits. Independent is also a jargony word. It means unlinked, not on the same chromosome, assorts independently. We're going to talk a little bit more about what this means. But in my case, I'm going to choose eye color and skin color. Now, for your example, you can choose different traits for your organism. And then we also have to assume that these traits have only, they're determined by single genes, and each gene has only two alleles, and those alleles are completely dominant. So in my example for eye color, I'm going to say that there's only two options. You've got green or gold as the traits, and the green version, the green allele, is completely dominant to golden. So that the only way to have golden eyes is if you have two golden alleles, one from each parent. Any other combination where you have two green alleles, one from each parent, or one green and one golden, or one golden and one green, that's going to still look green. So green's totally dominant to golden. Skin color, I'm going to say the two options are bronze and white, and bronze is dominant to white. So here is what a true breeding homozygous dragon would genotypically be and what it would look like. So if it had both the eye color alleles were big G for green, and both the body color alleles were big B for bronze, then it would look bronze with green eyes. There's lots of other combinations you could have, but the recessive dragon would have two recessive alleles for golden, but the eyes would be golden, and two recessive alleles for body color, which would be white. So the way to make a double heterozygote, this is not the only way, but the way we're going to imagine that it happened is that a true breeding golden bronze dragon, so he's homozygous, right? He's got two green alleles and two bronze alleles, mated to a golden-eyed white dragon. So had two golden alleles for the eye color and two white alleles for the body color. And the important thing to remember is, what do these genotypes mean? This is what the phenotype looks like, right? Well, one of the things it means is this dragon, because it's got two green alleles for eye color and has two bronze alleles for skin color, is only capable of making eggs or sperm that have big G, big B in them. Remember that when you make the gametes, the eggs or the sperm, you're only going to randomly pick one of these, and you're going to randomly pick one of these. You have two copies of these Gs, you have two copies of the eye color gene, you have two copies of the skin color gene. The gametes can only have one copy of each. So we randomly pick one of these Gs, but they're both the same, so you get big G. We randomly pick one of these Bs, but they're both the same, so we get big B. And similarly over here in the double homozygous recessive dragon, all the possible gametes, all the eggs and sperm from this dragon are going to be little g for golden eyes and little b for white skin color. If you mate these together, because all the gametes from this are going to be big G, big B, and all the gametes from this are going to be little g, little b, then you will get this double heterozygote, big G, big B, little b. It's not the only way to do it, but it's one way. And so now we have this dragon that's a quote unquote double heterozygote. It just means that at the eye color gene, there's two alleles. One is big G, one's little g. And one is big B and one is little b at the skin color locus. But the overall appearance of the dragon is still going to be the dominant appearance because the single big G and the single big B are dominant over the little g and little b. So that's the genotype of this double heterozygote, and this is its appearance. Your assignment will be to create an animal or plant or creature of some kind with two traits, and you're going to imagine what the double heterozygotes genotype is and what its phenotype is, and then you're going to take this double heterozygote and mate it to another double heterozygote. Now, it's important when you're doing this to think about what the possible gametes are from this creature. So when it's going to make eggs and sperm, it has more options than its parents had, right? Because every time you go to make an egg or a sperm, you're going to randomly select one of the G's and one of the B's. So what are all the possibilities? Well, maybe randomly you select the big G and the big B. So that's going to happen about a quarter of the time. But you might also randomly select big G and little b. You could also randomly select little g big B or little g little b. So these are all equally possible. When we do a dihybrid cross, what we're doing is mating two double heterozygotes together. And the one way to predict what their babies will look like is using a Punnett square. And it's the hardest way, but we need to do it at least once to believe the ratio that I want you to then memorize. So here's our double heterozygote dragon. He's going to mate to another double heterozygote dragon, and his possible alleles are all up here. And there's the other dragon that he's going to be mated to. They both have the same gametes, right? The same ratios of possible gametes. So we make a Punnett square that is a 4x4 grid, and we populate it with all these possible gametes. We say, well, what if this is the male dragon, and here are all the sperm options. And what if this is the female dragon? These are all the egg options, right? 1/4 of the time it's big G, big B, 1/4 little big G, little b, 1/4, et cetera, on both axes. And then we just fill in what would happen if this sperm and this egg were to meet. Well, then 1/4 of the time times 1/4 is 1/16. 1/16 of the time you would get big G together with big B, big B. If this sperm would meet with this egg instead, you would get this, and so on. You just keep going through all the things until you end up with a whole entire Punnett square populated. And the reason that each of these squares is 1/16 of the time is because there's 16 squares and they're all equally likely, right? So if it's equally likely that a quarter of the time you'll get this and a quarter of the time you get that, then a 16th of the time you get this. So we populate this whole thing, right? And these are all genotypes, of course, but they predict the phenotype. Right? This is the way to say what is in the DNA. Now let's look at these baby dragons. What do they look like? Okay, so let's look at the first type of dragon we could make, a green-eyed bronze skin colored dragon. That's going to happen every time there's at least one big G and one big B. We don't have to know the rest of this because these are dominant. So if we know we have at least one of these and one of those, then we're going to get this dragon. And so we look through our Punnett square to find all of those, and there they are, right? All of these have at least one big G. Some have both, some have one big G, one little g, but either way, we're going to get green eyes. Some have both big Bs, some have a big B and a little b, but either way, we're going to get bronze skin. So there's, how many of these are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, there's 9 out of 16 times we're going to get this phenotypic dragon. What about this one? Bronze skin, but with golden eyes. Well, that's going to happen 3 out of 16 times, right? We do need to have both of the eye color alleles be little g, because otherwise we can't get our golden eyes. But the body color could have just one big B or 1 or 2 big Bs, right? So either way, all of these are going to have the same phenotype, which is golden eyes with bronze skin. How often are we going to get this green-eyed dragon with white skin? That's going to happen 3 out of 16 times as well. So here we have those 3 out of 16 options. And how often are we going to get this rare white dragon with golden eyes? Just 1 out of the 16 times, right? And this is where this phenotypic ratio comes from. When you mate 2 double heterozygotes together in these very specific conditions we've talked about, the genes are not linked to each other, they randomly assort, there's only one gene that expresses each trait, it only has 2 alleles, one's completely dominant over the other. Like, the list of assumptions we have to make is long, but there are some genes that behave this way. And so if you mate 2 double heterozygotes together, as we've done here, then this is the expected phenotypic ratio. It's not the genotypic ratio, that's more work to say what that is, but it is the expected ratio of these visibly different dragons. Now, it's just a ratio. It's not like every time you mate these dragons, they only have 16 kids. What if they had 50 eggs and they all hatched? Well, we can predict our expectations for these different types of dragons by taking the ratio, right? 9 out of 16 times 50 will give you green-eyed bronze dragons. So 28 out of the 50 dragons we expect to be green-eyed with bronze skin. And we can do that same kind of math. We can say, well, 3 out of 16 times we're expecting this golden-eyed bronze dragon. So that's 3 out of 16 times 50 will give you a different number. It's important to understand that this is just a probability. This is our expectation based on the random chance. In reality, and you probably already intuitively know this, there's some random variation, right? If you think about the probability of, for instance, having boys or girls as your children, getting a boy or a girl is roughly equal, right? The likelihood is 50-50. But if you look at individual families, even very large families, you don't always see exactly 50-50. You might get close, but sometimes I've known people who have 5 or 6 kids and they get like a run of 4 boys and 1 girl or something. And that's because each event is sort of like just a random chance. So in order to see these ratios in order to see reality match the ratio more closely, you have to have a lot of kids, right? To sort of smooth out that randomness of what's happening. In any case, you don't have to worry about this part so much. What's your assignment? Make up an organism, decide 2 traits that you're going to follow, and assume that those traits are each coded for by 1 gene that has 2 alleles where 1 allele is dominant. Then draw the Punnett square as if 2 double heterozygotes were mating, and you can use my little walkthrough as a template, and bring that to class on Wednesday. All right, hopefully that has been helpful. I will see you Wednesday. Happy snow day.